So this is a video that I want to make. Today is April 9th. Today I originally had a worksheet planned. I moved it to a lecture day, and that was a bad choice, apparently. So what I want to do today is just quickly talk about some things from section 16.5 mostly. We did 16.1 last time. We've been talking about vector fields. So a vector field is basically an assignment to each point in the plane or in three-dimensional space. To each point we assign a vector. So for example, last time we looked at the vector field negative yx, and so for each value of x and y, we put that vector negative y comma x at that point. So starting at that point, and when you do that, you get these nice pretty pictures that look something like that. And we have basically two main operations that we can perform on vector fields, and the first is the divergence. So the divergence of a vector field was defined to be the partial derivative of p with respect to x plus the partial derivative of q with respect to y, where p and q are the components of the vector field f. So that was the divergence. And then we also last time talked about the curl. And this isn't really the curl. Curl is a three-dimensional quantity that we'll talk about soon. But the two-dimensional curl was q sub x minus p sub y. And the divergence is a measure of spread. And what I mean by that is that if you were to imagine that you have some sort of two-dimensional vector field, maybe you have like a very, very shallow stream or something, and you're trying to figure out how things move throughout the stream, the divergence is going to tell you how things kind of spread out over time. So if you were to have a positive divergence, that means that if you were to have the positive divergence at a particular point, that means that at a certain point, more stuff is leaving that point, leaving that neighborhood than coming in. If you have a negative divergence, your negative divergence means more stuff is coming in than going out. And these pictures might be a little bit misleading, but last time I showed you a video where you had a vector field where the vectors increased in magnitude as you go from left to right. This would also have a positive divergence because there's more stuff coming out than going in. So that's the kind of situation that we can have with a positive divergence. If the divergence is zero everywhere, we have a name for those vector fields. Those are called, F is called incompressible. We use the word incompressible because that's how we think of fluid flow. So if we were to model some sort of fluid flow, like we are trying to look at how, maybe some stream is moving, or if we're looking at how some body of water or a gas or something is moving, if we're modeling any sort of fluid, by fluid I mean a liquid or a gas, we would model fluid using an incompressible vector field. So if the divergence is zero everywhere, we call that vector field incompressible. And so the divergence is a measure of spread. If I were to give you the vector field xy, then the divergence of f would be 2. And that means that at every possible point, the vector field is acting as a source. Okay, so if the vector field has a positive divergence at a particular point, we call that point a source. So if the divergence at some point x naught y naught is positive, then the point, I'll call it A, which has components x naught y naught, is a source. It's as if stuff is coming into the vector field from that point. If the divergence is negative at a point, then we call that point A a sink. And I've already said this, I'm not going to write it again, but I do want to say it again. If the divergence is zero for all points, then we call that vector field incompressible. Okay, and so that's what we need to know about two-dimensional divergence. We also talked about two-dimensional curl. Curl really is a three-dimensional quantity, which we'll talk about in a second. But the two-dimensional curl is going to be q sub x minus p sub y, where your vector field that you're working with is the vector field PQ. Okay, and it turns out that curl is a measure of rotation. If I think about a two-dimensional vector field, so let's say I have a two-dimensional vector field, and what I want to do is I want to put in into that two-dimensional vector field, so maybe I have a very shallow stream, and in that stream I want to place a stick. And what I'm going to do is I'm going to put a little pin in the middle of that stick so that the stick stays in place, but then the stick is free to move. The stick is free to move in whatever. It can go counterclockwise, it can go clockwise, it can go really fast, it can go really slow. And so if the stick is free to move, but the center of the stick stays where it is, then the curl tells you the direction and how fast that stick is going to move when it's centered at that point. Okay, so the point here, the xy value here is the point at which this thing is centered. And then the curl is a measure of how that rotates. If the curl is positive, then we have a counterclockwise rotation. Okay, so moving in a positive direction for mathematicians for whatever reason means counterclockwise. Just think trigonometry. Okay, so if the 2D curl is positive, then we have a counterclockwise rotation. If the 2D curl is negative, then the rotation is clockwise. So that would mean that the stick that you put in the stream is rotating clockwise. And then the magnitude, in this case what I mean by that is the absolute value of the curl tells you how fast that stick is rotating. If the curl is 0 for all values, if the curl is 0 at a particular point, then F is called irrotational at that point. Let's call it A again, X naught, Y naught. Okay, so if the curl is 0 at a point, we call that point irrotational. All right, we could do some examples here, maybe one or two. For 2D curl, if I have a vector field which is X, Y, then the curl would be the partial of Q with respect to X minus the partial of P with respect to Y. And we would get 0 minus 0 or 0. If you have the vector field negative y comma x like we worked with before, then the 2D curl would end up being the partial of x with respect to x minus the partial of negative y with respect to y, which would give you 2. Okay, so we would have, in this case, since the curl is positive, we would have counterclockwise rotation in that vector field. This vector field, negative y comma x, is the one that we looked at in class yesterday. So because I have my iPad, I can do that. And so if you actually look at that vector field, it makes sense that this actually really is moving in a counterclockwise manner. Okay, and so that's the curl. Now, curl and divergence, really, we should make sense of these in 2 and 3 dimensions. Before we get to the 3-dimensional stuff, I want to remind you that the gradient of a vector, so the gradient of a function, let's say that I have f of xy, the gradient of this function is defined to be a vector where we have the partial derivatives in each component. So if I have a function of 2 variables, that's going to be a 2 vector, right? A vector with 2 components. Each component will be the partial with respect to x and the partial with respect to y. So that's the gradient of the function. And what I want to do is I want to think about what this del operator is doing. This del operator we can think of as the derivative with respect to x, the derivative with respect to y. That's not really a vector, but it's really a function. Or I guess you could think of it as a vector whose components are functions or operations. When I say an operation, what I mean is you're going to apply that operation to a function, and then that operation says do something. In this case, it's take the derivative with respect to x, or take the derivative with respect to y. When we have vectors, we have basically three different ways of multiplying. I could take a vector and I could multiply by a scalar, and that's going to give us scalar multiplication. So we just get 4, 8, right? We just take 4 times 1, 4 times 2. So that's scalar multiplication, and that's the kind of thing that we get when we apply this del operator to a scalar valued function f. Remember, this is a scalar valued function because the output is a scalar, it's a number. Okay, so that's what happens when we apply this del operator to scalar valued functions. If we apply this del operator to vector valued functions, then we have two different notions of multiplication. The first is a dot product. So let's think about what happens when we have a vector field PQ. And then we look at what's the gradient, the del operator dotted with, so take the dot product with f. So we're going to have the partial with respect to x, partial with respect to y, and then we're going to dot that with f. And here, what I mean by multiplication is it's going to look like multiplication, but it's not really multiplication. Right? We're going to take the product of the first two terms plus the product of the last two terms. Again, by product, I don't really mean multiplication. I just mean apply that operator to P plus apply the other operator to Q. So 1 to P, 1 to Q, and then add them up like we do for any dot product. And what this gives us is the derivative of P with respect to x plus the derivative of Q with respect to y, which is nothing more than the divergence. And the dot product is defined for vectors of any dimension. Okay, so it turns out that the divergence is defined for vectors in any dimension. So we can think of the divergence of a vector field as applying the del operator to a vector field f. Okay, so that's our first thing. The next thing to talk about is we have one final notion of taking a product, and that would be the cross product. And cross products are only going to be defined in R3. So that means the actual curls or cross products are also only defined in R3. Okay, it turns out the cross product of this del operator with our vector field will be the curl, also defined only in R3. And so what ends up happening is if I take the del operator and I take a cross product with the vector field f, like I said before, this is called the curl. Whenever I talk about curl, this is always a 3D quantity. Okay, when I take the divergence or the dot product of two vectors, you got a scalar, which makes sense. When you take a curl or a cross product, you got a vector. And this is really only an operation that's defined in 3 dimensions. And so this is going to be the determinant. Remember, the way that cross products work is that we put I, j, and k across the top. In the second row, we put the first vector, which in our case is the del vector. And then in the bottom row, we're going to put the last vector, which is our vector field f. Let's say that our vector field f has components p, q, and r. So that would mean that we would put p, q, and r. And what's going to happen is we're going to get I times, let's cross off that row and column. It's again going to be that same, it's not exactly a product, but we're going to take, it looks like it, we're going to take the derivative of r with respect to y minus the derivative of q with respect to z. Okay, so that's what we get for the I coordinate, because we cross off that row, that column, and then we get the product of those two terms. Just like any determinant, we're going to have an alternating sign. So we'll get minus j, and then we cross off that row, in that column. We'll have the derivative of r with respect to x minus the derivative of p with respect to z. So we'll have the derivative of r with respect to x minus the derivative of p with respect to z. And then finally, our last component that we'll have will be a plus k. So we'll have a plus k. And if we cross off that row and that column, and then we'll multiply by the determinant of the 2 by 2 submatrix, so q sub x minus p sub y. So we'll get the derivative with respect to x of q minus the derivative with respect to y of p. And if we clean all this up and write this as a vector, this is going to be the derivative of r with respect to y minus the derivative of q with respect to z. For the middle component, we'll have the derivative of p with respect to z minus the derivative of r with respect to x. And then for the final component, we'll have the derivative of q with respect to x minus the derivative of p with respect to y. And so that is called the curl of the vector field F. This is a process that should just be done each time. So just find that cross product. Do not memorize the formula. The only thing that you need to memorize, or it's not even really memorizing, the only thing to know is that the curl is that cross product. Okay, and so maybe what we'll do is I'll give you a vector field, and then we'll compute the divergence in the curl, and we'll go from there. The curl in 3D, so the real curl that we're talking about, like true curl, is a little bit harder to describe intuitively, but the idea is that it tells you it's a measure of rotation. So what we have to kind of picture now is that you have some sort of three-dimensional vector field. Maybe you have like an ocean or something, and your vector field is going to be, let's think about it like a velocity field. So the vectors will tell you in which direction to move and how fast. If you were to drop a bunch of sand in an ocean at a point, maybe, it would tell you how fast to move in and what direction. And what the curl is going to do is, if you were to imagine that you have a stick in an ocean and it's the center of the stick is fixed in place, but it's otherwise free to move around kind of in, not just in 360 degrees, but also, not just in the XY plane, but also in the Z coordinate as well. So it can rotate really, if you were to imagine a stick kind of in the ocean kind of rotating all around, it would eventually trace out a ball or a sphere. So as long as that stick stays in the same place, what the curl is going to do is it'll tell you the direction that that stick needs to be so that you're moving in the fastest way possible. Okay, so you can imagine if you have a stick in a vector field that maybe one way that you hold the stick is moving a little slower than in another way. The curl is going to tell you the direction that you have to hold the stick so that you are moving the stick as fast as possible. Okay, so it's a little harder to visualize, but I feel like that's worth explaining, at least intuitively, a little bit. You don't have to worry too much about intuitiveness of curl. I think we'll mostly rely on rotational density for our intuition. Now, let's do one example and we'll be done. Let me give you a vector field that's maybe xy plus z, x plus z, and y squared. And I want to compute the divergence and the curl of f. And the divergence is pretty easy. That's just going to be the del operator dotted with the vector field, which in our case is ddx, ddy, ddz. So dotted with our vector field xy plus z, x plus z, and y squared. And if we take the dot product, that means that we're going to multiply each corresponding component, and add them up. By multiply, I mean we're going to take the operation, so it's going to look like multiplication, but it's not really multiplying. So we're going to take the derivative of xy plus z with respect to x, the derivative of x plus z with respect to y, and then the derivative of y squared with respect to z. And when we do that, we're going to end up with a scalar quantity that's going to give us y plus 0 plus 0. So it turns out our divergence is just y. For the curl, this is going to end up being that del operator cross product with our vector field f. For that cross product, we'll need to find a determinant. This will be the determinant of, let's see, we'll have I, J, K. We'll have our ddx, ddy, ddz. And then in our final part, we're going to put our vector field itself. So we have x, y plus z, x plus z, y squared. And so when we compute this determinant, we're going to end up with I times the derivative of y squared with respect to y minus the derivative of x plus z with respect to z minus j times the derivative of y squared with respect to x minus the derivative of xy plus z with respect to z, and then plus k times, let's see, we're going to have, when we expand along the third row, third column, we're going to have the derivative of x plus z with respect to x minus the derivative of xy plus z with respect to y. And so altogether, what we're going to get is, we'll get 2y minus 1 for the first component. The second component, we're going to have a negative, and the derivative of y squared with respect to x is 0. The derivative of xy plus z with respect to z is 1. So altogether, that's a negative outside the parentheses, and then 0 minus 1. And then for the third part, our k term, we're going to have the derivative of x plus z with respect to x minus the derivative of xy plus z with respect to y. And so that'll be minus x. And so altogether, the curl that we're going to get here is 2y minus 1, 1 minus x. Okay? The terminology that we're going to use for the divergence and curl in 3D is the same as 2D. So if you have a point at which your divergence is positive, that's a source. If you have a point where the divergence is negative, that's a sink. If you have a vector field that always has a divergence of 0, then that's an incompressible vector field. Okay. Likewise, if you have a point at which the curl is 0, then that's called an irrotational vector field. Okay, so all the terminology will be the same. All right, so I'll leave it for there, and we'll pick up on class on Thursday. Thanks.